So we're starting chapter 3. We have an exam coming up. It will not, we're not getting all the way through chapter 3 for the exam. We're just getting through the first part. I will tell you where the cutoff is. It is announced in Blackboard where the cutoff is in my notes. But this is typically, keep in mind, typical semesters cut into quarters. And I know how far I can get in a quarter of a semester. So this matches the cutoffs. It varies a little bit forward and back. Sometimes I don't get quite as far, but I can actually, mark myself for where I'm going to get to this semester. Sometimes it's tricky. One of the things we don't have is we don't have a room full of people who could be asking questions. And that has a tendency to slow me down. So if you add up all the times for these videos, it doesn't necessarily add up to what would be full lecture times. But that's because nobody during these lectures is asking me questions. As always, feel free to ask me questions on email, and I will, if we go back and forth and it doesn't seem to be working, or I think other people have the same question, I may put a little video up in these files so that to answer those questions. Some of you may know at this point, now we haven't even gotten to the semester yet. It's still the end of August when I'm doing this, but they're closing the campus down for Friday cleanings, which I gotta say doesn't really completely make sense, because the virus, if we're going from Thursday to Monday, pretty much everything I've read would indicate that there are no viable, as in infectious viruses still on a surface after 4 days, but they want to clean the place on Friday, so I'm not going to be here on Friday for you to call into the lab. And it could be wrong. Maybe the virus can last a little longer than that. This is where it starts to get a little crazy. We're dealing with things that are too tiny to see even with our microscopes. They're too tiny to see even with the best microscopes in the world. You can see an atom, but you can't see the bits and pieces of it. You can see them at work, you can see them at play, you can figure out what they're doing, but you can't really see them, and it produces, it makes them concepts that can be hard to wrap your head around. So I've said that this can be a difficult course. This is part of the reason, where you have to just kind of grasp what we're talking about. Now, an atom, and I'll write this down a little bit, is the very smallest part of an element that is still the element. So if you have a completely pure lump of iron and you keep whittling away at it, the very tiniest piece that you could have that's still iron is an atom. You start chopping at this, it stops being iron after that. Whether it's oxygen or hydrogen or carbon or iron or whatever it is, there'll be an atom that will be that element. When you start to stick elements together, like water has hydrogen and oxygen in it, then the smallest piece is going to be a molecule. So this is chapter 3. So water's a compound. H2O, 2 hydrogen atoms and an oxygen atom bonded together. Carbon dioxide, 1 carbon and 2 oxygens. Carbon monoxide, 1 carbon and 1 oxygen bonded together. Is that tremendous number of things are more than 1 atom stuck to one another, and when you stick them to each other, they act differently. Right? Water is hydrogen and oxygen. It doesn't act like hydrogen gas, it doesn't act like oxygen gas. You put them together, the bonding makes for a new thing that acts differently than the things that they're part of. It gets tricky. And we'll talk about how the bonds work and what sticks them together and all sorts of things later on. We're going to start by looking at the parts of an atom. Inside is the nucleus. There's two different types of particles that can be inside a nucleus. And for most nuclei, it's got at least one of each of the two types of particles. For chemistry, which is what we're working our way into, the nucleus is not a huge player. The fact that it has a positive charge that kind of holds on to the negative charges of what's zipping around the nucleus that aren't part of the nucleus, that's about it. And there's a couple of other ways that a nucleus can be important. But there are two different types of particles that are inside a nucleus. That said two particle types. I know I moved it fast, but this is a video. You can go back and freeze it. I won't write this stuff down, but this pretty much covers it. There are protons, little positives on it. Protons have a positive charge. Each proton has a single positive charge. And there are neutrons, which are in there that don't have any charge, but are very instrumental in holding the nucleus together. If you know anything about magnets, you know if you get the two positive ends of a magnet against another one, they repel each other. We have all these positive charge particles stuck in this tiny little space. They need help to stay together. And the neutrons are very important in stabilizing and holding the nucleus together. And we're going to deal with that for a bit. The electrons are outside, going around at different distances. We'll come back and talk about the electrons. As it says here, the nucleus consists of neutrons and protons. For people who don't realize this, sometimes I point with my shadow. So we got protons. These are very, very tiny. People realize pretty quickly that the things we use in the world to weigh things, you are getting such tiny fractions of that when you're dealing with atoms, that they kind of went, well, let's come up with our own measurements that we can apply to the atoms. When we know we got these particles in there, why don't we take the proton and make it the basic unit? 1 unit of atomic weight or mass is going to be, a proton has 1 unit of atomic weight or mass. So if there's 3 protons, then there's 3 units of atomic weight or mass. Each proton has 1 positive charge. The total number in any atom equals the atomic number and it determines the element. What makes iron iron? It has a certain number of protons in the nucleus. And that's it. What makes hydrogen hydrogen's got 1 proton. What makes helium helium's got 2 protons. What makes lithium lithium, it's got 3 protons. I don't know. I don't have all these memorized. But if the number of protons changes, and there's certain types of emissions, radiation emissions from a nucleus that can change the number of protons, then you've changed the element. The element changes from one element to another. If you lose anything else, as long as it doesn't change the number of protons, it doesn't change the element. Now there are, I'll come back. This is one of the things that I hand out. There's a whole bunch of variants of this linked to in the book. And I will put, well, there's all bunches of links in the book. So you can find all of these. The one that I use is out of the back of an old chemistry book. I kind of like it because it prints well, but you can find this information all sorts of places. So in these boxes, down here it says atomic number. So if the atomic number is, and it's hard for me to read off of the screen, if silicon is atomic number 14, this is silicon, atomic number 14, then every atom of silicon has 14 protons. If it doesn't have 14 protons, not silicon. And there's all sorts of variations on this. I really needed to grab, I'm gonna walk across the lab and grab myself a copy of this that I can actually read. So potassium has a 19 here, it's atomic number 19, it's got 19 protons. Iron, out here, is number 26. It would have 26 protons in the nucleus. Neutrons are also in there. They have no charge. They have 1 unit of atomic mass. They stabilize nucleus. The number of neutrons in an atom might vary. It can't vary too widely because it's important in stabilizing the nucleus. And so there's some numbers just won't fit in there. There's just so unstable that it's just not, you don't find them that way. But you do find atoms of the same element that may not weigh the same thing, that may not have the same number. It's always got the same number of protons, but it may have different numbers of neutrons. And those are isotopes. Isotopes are variants in an atom that weigh different, and in some cases are different stabilities. This is when it starts to get important. The numbers on the top of these boxes, and for an awful lot of periodic tables that you can look at, including periodic tables that I've linked to in the book, these are not whole numbers. The atomic mass at the top of the box is not a whole number. But if it's the number of protons and the number of neutrons added together, because it turns out the electrons don't weigh anything, how can you add a bunch of single units and a bunch of other single units and not get a whole number? It's because in the world, like carbon. Carbon does not exist as a single isotope across the world. It has, there's carbon-12 and carbon-13 and carbon-14, mostly carbon-12. Carbon-12 is by far the most stable, is the most stable of them. So most carbon out there is carbon-12. But there's carbon-13 and carbon-14, and what they try to do here is kind of average all the numbers of, there's this much 12 and this much 13 and this much 14, and it gives you a number for carbon, like the number for carbon is 12.011. What does that tell you? Well, if you round it off, you get 12. That's going to tell you 12 is the most common and probably the most stable of the isotopes of carbon. And for the lower part of the periodic table, the part that's here before you hit the bridge. So these elements and these elements, all of the numbers are very close to a whole number. And that's how you figure out the weight of the most stable isotope. For oxygen, it's 15.999, so 16. Oxygen is atomic number 8. Got 8 protons. If its most common isotope is weight of 16, it's got 8 neutrons. Phosphorus is 30.97 something. So that rounds off to 31. Phosphorus is atomic number 15. That means it's got 15 protons in it. Well, how many neutrons? Well, what's 31 minus 15? The most common stable isotope of phosphorus has 16 neutrons. 15 protons, 16 neutrons adds up to that 31. We rounded the number at the, off to in the atomic number. So the easiest thing to do with atomic numbers that are fractional is round them off. And for our purposes, that will work. When you get into this bridge here, it turns out there's a couple of different stable isotopes. And so the numbers are not, really close to a whole number sometimes. We're not going to worry about those. Is that the chemistry that happens when you get into these bridges gets bizarre. I will talk about it, but we're not going to really get into that. And so we're going to ignore some of the weirdnesses of the isotopes as well in there. Typically, number of protons tells you the element, the atomic number. Number of protons plus number of neutrons gives you the overall mass or weight of the atom. Usually it's given fractionally because they're doing weird things with the isotopes in the world. You round it off to the nearest number, subtract the protons, gives you the number of neutrons. You'll notice if you look at old exams, I ask questions about that a lot. That, I believe, is a good place to stop. We'll pick this up with isotopes of carbon in the next video.